Okay, so I'm Rafael, and I'll talk about barriers for rank methods in arithmetic complexity, and this is joint work with Klim, Ankit, and Avi. Okay, so I'll start with the big picture, I'll add into what Krista said, and then I'll explain to you how we prove general lower bound techniques in arithmetic complexity. I'll explain the rank techniques, which have pervaded CS conferences in the past 7 years, and then I'll just give you a simple example of one of the first arithmetic lower bounds. Okay, and then I'll proceed to show our results, but this is just the introduction. So, what is a barrier? Well, how do we prove lower bounds? You can think that any lower bound is, you pick a property P, and then you should say, well, polynomials that can be computed, easy polynomials, they possess this property P, and then you try to find some polynomial or some Boolean function that doesn't have the property P, and then you obtain your lower bound. Okay, so for example, here's a property. Given a function f, let L of f be the minimum size of a formula computing f. Okay, this is a property of f, and the property Ps, if I give it this parameter, s, is the minimum formula size is less than or equal to s. Right? So obviously, this would give us lower bounds, right? Because if I find a function that doesn't have this property, that's a definition of a hard function. But of course, it's obviously hard to characterize this property, right? So it's pretty bad to give lower bounds. But a barrier is the following. A set of techniques, so a technique would be a set of properties P, cannot prove a non-trivial lower bound on a certain computational model. For example, formula size or some other models that we'll see, okay? So a barrier is just saying that certain techniques cannot prove non-trivial lower bounds. Okay, now how do we usually prove lower bounds? Well, we usually tend to think of progress measures, right? Even in the Boolean case and in the arithmetic case. So the idea is that computation progresses slowly. And then we capture progress with some function that grows slowly with each basic computation. So for example, mu, we pick a measure mu, such that mu of f, any operation, plus or times, g, is less than or equal than mu, the measure on f plus the measure on g, okay? And star is any basic operation. And we also need that this measure mu lower bounds the minimum formula size for any function phi. So once we do that, we find this progress measure mu, we find an explicit function f which has really high measure, and then we can prove the lower bound that any formula f must have size at least mu of f, because the measure lower bounds the formula size. So far so good. Then, again, just repeating barriers with a little bit more notation, you pick f being the set of progress measures mu, and then c is a class of functions, let's say class of polynomials computed by small circuits or small formulas, and then a barrier is mu of f, so any measure mu in f, for any measure mu in capital F, mu of f is small, for any polynomial f in C. Okay, so that's what a barrier is. Now, what can progress measures achieve, right? So in the arithmetic setting, because we are a little bit more restrictive, it's easier to prove lower bounds. So let's see what we have achieved. So in the bounded depth regime, we have had remarkable advances. So starting with the work of Gupta, Kayal, Kamath, and Saptarishi, we know n to the square root d, lower bounds, for homogeneous depth for circuits, okay, for polynomials in n variables, and degree d. Okay, so throughout the talk, n will be the number of variables of your polynomial, and d will be the degree of the polynomials. And you can stop me at any time if you have questions. Now, in 98, Grigoriev and Karpinski, they also proved a lower bound of n to the d for depth 3 circuits over small finite fields. And in 2017, Landsberg and Ottaviani, they proved n to the d over 2 lower bound for diagonal depth 3 circuits, which I'll describe later in the talk. You don't need to know what they are right now. And in the multilinear setting, we also have impressive lower bounds. However, none of these lower bounds, when we go to the general setting, imply anything much better than what we had since the 80s. So in the even though we have remarkable advances, in the general setting we have very little progress, even with the techniques above. So for example, we cannot beat Bauer-Strassen's lower bound of n log n for general circuits. Okay, and you can see, and for tensors, for example, this work of Alexeyev, Forbes, and Zimmerman, they prove a lower bound of 2 to the n to the d over 2 for d-dimensional tensors of side n. Okay, and notice that the trivial lower bound on the tensor rank is actually n to the d over 2. Okay, so really far from proving anything remotely surprising. So what's the punchline of this slide is that bounds 1 and 2, they're very far from bounds for random polynomials. Okay, so even the 1 here, even with the remarkable advances in step 1, okay, the lower bounds that you can get for those models of computation for random polynomials, they're much larger than the bounds that we proved so far. Okay, so the bounds in 1 and 2, they're very far from the bounds that we know for random polynomials. And this begs some explanation. Why is this the case? Why, even with such impressive lower bounds, we're still very far from proving any lower bounds for any function, never mind explicit functions. And the third question is, are there techniques from 1? Are these techniques that we use in 1 limited in the general setting? And we don't know. So let's just draw the parallel, as Christo said, with the Boolean world, okay? So lower bounds are harder to prove in the Boolean setting, so it should be easier for you to find barriers, right? Because barriers is the impossibility of proving lower bounds. And that's true, right? So we started with Baker, Gill, Solovey with relativization, and then Aronson and Vigderson with an extension of relativization, and Razborov, Rudich with natural proofs, right? So they state that progress measures, similar to what we're going to do now, which are natural, they cannot separate pre from NP. But notice that in Razborov, Rudich, their natural proof, it's a conditional statement, okay? It's based on the efficient construction of PRGs, okay? And here now, we want unconditional barriers, right? We don't want to have any assumptions. Now, in the Boolean setting, it's much harder to prove lower bounds, so barriers should be easy. In arithmetic setting, it's easier to prove lower bounds, so it should be harder to find barriers. And that, up to this year, was actually the state of things, right? So, since 2009, Aronson and Drucker and Groschow, they started looking for barriers, and what their idea was is to try to encapsulate all the lower bounds, to unify, as Christos was saying, to unify all the lower bound techniques in a mathematical way. And what they did is they said, let's represent all the polynomials by a list of coefficients, and then any lower bound technique is some algebraic variety in this coefficient space, in this list of coefficients, okay? So you can think of it as zeros of polynomials, okay? So they said any lower bound that you can prove, they can be captured by zeros of polynomials in this other coefficient space, okay? In the space of list of coefficients of the polynomials. So they provided this unification for us, but they didn't provide any barrier. They couldn't find any barrier. And then, building on the works of Groschow, Forbes, Puke, and Volk, and Groschow, Kumar, Saraf, and Sachs, they gave us this idea of succinct lower bounds, okay? And I won't describe what it is, but essentially they said that if you don't have any succinct hitting sets, this is equivalent to finding a barrier, okay? So I won't describe much, but the punchline here of their works is that they provided us with another way of getting barriers, but they did not have any complexity assumption to back up this claim that we can provide barriers, okay? So even though we had these models, we still don't have any even conditional statement saying if such complexity result holds, then we have barriers, okay? And this is the state of affairs. Now, let me talk a little bit about the general lower bound techniques and a little bit of what we do, okay? So, throughout all the lower bounds that I mentioned to you for low depth circuits, they all go in this way, okay? So you pick a polynomial and you decompose it into some of the simpler polynomials. And then you come up with the progress measure that is just subadditive, okay? So mu of f plus g is less than or equal than mu of f plus mu of g. And you know, you have to define what simple polynomials are, but essentially simple polynomials are these polynomials such that mu is small on all of them, okay? So you come up with a definition of simple polynomials, come up with a progress measure mu that's small in the simple polynomials, and then you only need to find some explicit polynomial with high measure. Okay? So let me show first what examples of decompositions are. So Highfield in 79, he just showed that if f is computed by some homogeneous circuit of size s, then you can decompose f into polynomials g1 up to gs, where each gi is highly factorable, right? So it factors into at least two factors, pi and qi, where the factors are of low degree. Okay, so that was Highfield's definition of simple. Okay, polynomials which factor. Tensor rank is the one that you're most familiar with, right? So if f is a tensor of rank s, then what is the decomposition? The decomposition is into rank 1 tensors. Okay, a rank 1 tensor is a simple object, and the rank is exactly the sum of s of them. Now, as I promised, Waring rank. If I give you a homogeneous polynomial f, again, n variables in degree d, the Waring rank of the polynomial f is the minimum s such that f can be written as a sum of powers of linear forms. Okay, so each gi is a power of a linear form. That's what the simple polynomial is. So far, so good. And for all the bounded depth circuits that we saw lower bounds, that I showed you the lower bounds, their decomposition is this. If f is computed by some depth h circuit of size s, then you can write f as a sum of polynomials gi, where each gi is computed by a depth h minus 1 circuit, okay, with a product gate on top. So it's a product of many other polynomials of depth h minus 2. Okay, so these are some decompositions. I'm just going to talk mainly about tensor rank and Waring rank. So you just need to pay attention to those two. Now, again, how do we do the techniques with a little bit more symbol, right? So let S be the set of simple polynomials, and S hat is the span of S. Okay, so you just pick all the linear combinations of S. So we'll say that the S complexity of any polynomial f is the minimum S, such that you can decompose f into a sum of these polynomials, all of these polynomials being in S. Okay, I realize that there's too many s's in this slide. So, okay. And then a subadditive measure is, again, a measure from the space S hat, such that, well, subadditive, right? Now, if you let mu of t be the maximum measure in any subset t, the lower bound that you obtain is the S complexity of any polynomial is the measure of S, is the measure of f, over the maximum measure over the set of simple polynomials, right? Because you can just say, well, each of the GIs will have maximum measure in your set S. Okay? Now, let me show you a concrete technique that I think most of you are familiar with, okay? Which are rank methods. So rank methods is any measure which can be stated as the rank of a matrix, okay? So, okay, so this measure is the following. So you pick any polynomial, and you say, well, map this polynomial, pick the coefficients of the polynomial, map it into a matrix, and then you take the rank of that matrix as the complexity measure, okay? So this idea includes partial derivatives method, and shifted partial derivatives, evaluation dimension, coefficient dimension, and flattenings, which is something that algebraic geometers care a lot about. Okay, I'll show you an example in the next slide, so just bear with me for a second. Okay, so this was used in many works. So here's an example. So you have the partial derivatives, and let's just look at homogeneous depth 3 circuits. So the simple polynomial is just the product of linear forms. Now what is the measure? For any polynomial f, pick the matrix of partial derivatives where each row, okay, is the partial derivative with respect to that monomial. Okay, so for example, L of x squared minus y squared, you pick the derivative with respect to x and y in each row, and then you have that matrix, and your measure is the rank of that matrix. Okay, so how does the lower bound go? Well, mu of f is the rank of this matrix, of the partial derivative matrix, and for any product of linear forms, your measure is less than or equal. If you take just the partial derivatives of degree d over 2, right? So your measure is bounded by 2 to the d over 2, so it's pretty small quantity. And the measure for the elementary symmetric polynomial is actually really high. is roughly n to the d over 2. And therefore, the S complexity is again 3 divided by 2, and you get roughly this n to the 2 lower bound. Okay, n to the d over 2. Now, let me just state our results and put them into perspective. Okay, so our first theorem is that rank methods cannot prove a lower bound for tensor rank. Okay, if we just look at tensor rank, rank methods cannot prove a lower bound better than n to the d over 2. Okay, n to the floor of d over 2, that floor is important, on the tensor rank of any d-dimensional tensor of side n. Notice that we're not requiring anything to be explicit, even for random tensors. Okay? In particular, they cannot prove superlinear lower bounds for three-dimensional tensors. Okay? Actually, they cannot prove even better lower bounds than 6n when d is equal to 3. And d here is the dimension of the tensor. So if I pick three-dimensional tensors, I cannot even prove superlinear lower bounds. Okay, so this really kills all these approaches for tensor rank. Now, notice that this is a constant factor away from trivial. Okay? Well, we know there's very trivial tensors with rank n to the d over 2, which you can get from flattening. And for random tensors, we know that there are tensors with n to the d minus 1. Random tensors have n to the d minus 1 rank. Okay? And for complexity reasons, the bound needed for formula lower bounds, according to Run-Raz, is n to the d, the 1 minus little o of 1. So we're really far within this approach if you just use flattenings, if you just use rank methods to prove any formula lower bounds. Okay? And for Waring rank, we show that rank methods cannot prove a lower bound better than n to the d over 2 again, okay, on any n-varied polynomial of degree d. Okay? And this actually is very impressive because it almost matches the best lower bounds achieved by such rank methods that were just obtained last year by Lensberg and Ottaviani. And it's also a quadratic factor away for random polynomials. We know that random polynomials have at least 1 over n times n to the d. This is roughly n to the d lower bound. Okay? So this shows that really far from, even for this very simple model, to prove lower bounds just even for random polynomials. Okay? So I would like to just leave with open questions saying, well, can we extend this barrier to other circuit classes? For example, we are really trying, we know that now general depth 3 circuits are as general as any general circuits. Can we extend this barrier to, let's say, just depth 3 unrestricted circuits? And can we consider other mappings? And the other question is, can we develop techniques which do not fall into this rank method so we can escape this barrier? And I guess I'm out of time.
But we have time for questions while Josh sets up. Questions? Do we have examples of non-rank techniques?
Yes, we do. So, sorry. Yeah, I'll keep this in. Yes, we do have this one. Yeah, we do have some techniques from geometric complexity theory, like
for example, Strassen's for symmetric functions.
Right, and then we also have some new techniques from GCT that Burgiser and Eikemeyer, like these obstructions. They are techniques which we don't know if they fall into the rank methods. So we do have some. They still don't prove like high tensor rank, for example. They also prove linear bounds. Yeah, but we do have some.
Any other questions? Let's think of